In the previous section, we got started with the basics of supervised machine learning. In section 2, we're going to dive into the guts of several popular supervised learning algorithms within the parametric modeling family. We'll start this section by formally introducing parametric models. Then we'll introduce two very popular parametric models, linear and logistic regression. We'll spend some time understanding the inner workings, and then we'll jump into Python and actually code them from scratch, where we're going to introduce the concept of parametric learning algorithms and linear regression in particular. First, we're going to define what we mean by parametric, since that term has come up several times now. And next, we'll cover the concept and math behind linear regression. When it comes to supervised learning, there are largely two families of learning algorithms: parametric and non-parametric. This area also happens to be a hotbed for gatekeeping and opinion-based conjecture regarding which is better, but we're not going to get into that. We're simply interested in understanding what parametric models are, and simply put, these bullets kind of cover it. So they're finite dimensional. This means that they can learn only a defined number of model parameters, typically predefined. Related to that, their learning stage is typically categorized by learning some vector theta, which are also called coefficient. And finally, the learning function is often a known form, which hopefully we can clarify later in this video. Now, those first two bullet points are pretty closely related, so let's drill into those. If we go back to our definition of supervised learning, recall that we need to learn some function f. A parametric model is going to summarize the mapping between x, our matrix, and y, our target, within a constrained number of summary points. These number of points is typically related to the number of features in the input data. So if I have three variables in, f is going to try to summarize the relationship between x and y given three values in theta. These are called model parameters. So we have this question at the bottom here. Imagine we're asked to estimate the price of a house given its square footage and number of bathrooms. How many parameters are we going to need to learn? We'll come back to this in a moment. But before giving away the answer to our question, let's back up and explain some of the characteristics around parametric models. Something we've already covered is the fact that they learn coefficients or other model parameters generally constrained to the same dimensionality as the input space. Furthermore, given that characteristic, they tend to be fairly explainable since you can point to a variable and its corresponding parameter value and typically learn something about variable importance or its relationship to y, our target. And finally, they are conventionally very fast and do not require as much data. So at the end of this section, we'll go into a little more detail about that, but in the first few videos, let's leave it at that. So now we're back to our question from before. How many parameters will we have to learn for our example? Well, given square footage and number of bathrooms, we'll have to learn 2. So our function can be expressed as the estimated price given two variables, square footage and number of bathrooms, given two parameters, P1 and P2. So P1 will be the relationship between square footage and price, and P2 will be the relationship between number of bathrooms and price. Here's a quick problem setup in Python. x1 is our first variable, number of square footage. You can see we range from anything as small as 1,200 to as high as 4,000, and our price ranges anywhere from 200,000 to 500,000. In x2, we have the number of bathrooms, and these range from as few as 1 to as many as 4. Now you can see from our plots that there seems to be a positive trend going on here, and that makes sense, but we're going to find out as we dig into this example. So we want to learn some function that estimates price, and that function is simply going to be the inner product of our estimated parameters in each row vector of our data. So if you've not already guessed, we're performing linear regression here. Linear regression can conveniently be solved by using the least squares equation. Since we technically have an infinite number of possible solutions to this problem, least squares is going to find the solution that minimizes the sum of squared error. So here we complete our least squares on x and learn our parameters in the first cell. Then in the next cell, we're multiplying x by the parameters theta that we just learned to get the predictions. It's that simple. So if you really dig into it, there's only one home that we grossly underestimate in value, and that's the second to last one, which is 1,200 square foot and 1 bathroom. So it's probably an apartment. And maybe it's located in a really hot part of town, which is why it was priced so highly to begin with. In which case it would be a good variable if we could introduce that rather than just have the two that we currently have. So maybe we could create a better model if we had, that additional variable there. Now to pick apart our parameters, there's something a little bit funky going on here. If we read this equation in plain English, something doesn't quite make sense. So this reads, for each square foot we add to our house, the estimated price jumps by $142.58, which intuitively, maybe that makes sense. It's a hot market, maybe that makes sense. However, for each bathroom we add, our house decreases in value by $24,000. There's another conundrum here by this logic. If we had a house with 3,000 square feet and 0 bathrooms, it would be priced in the ballpark of what a 4,000 square foot home that has 4 bathrooms is. And that doesn't make a whole lot of sense. So there's obviously some limitations with our model here. So obviously when we try to summarize the mapping with so few features and so little data, there are going to be some non sequiturs that can emerge. But there are some other factors that we didn't consider that can help us out when we're fitting our linear regression. First of all, we did not fit an intercept and we did not center our features. So if you go back to middle school or even early high school algebra, and you remember that when you're fitting your line on a Cartesian plot, the intercept is where the line intersects the y-axis, and we did not fit one of those. So we can do that right here. So here we've done the same exact thing, but this time we have centered our data before solving the least squares, and we've estimated an intercept, which is simply the average of y, the actual prices, minus the inner product of x bar, which are the means of the columns of x, and the estimated parameters. This means if we had a house with 0 square feet and 0 bathrooms, it would still run us $52,000. Now obviously this is still a little bit silly, but in the scope of things it makes more sense than the previous scenario, right? And the predictions make a lot more sense when we use this intercept in the range of possible values, because maybe then you're still getting charged $52,000 for a lot with nothing on it. Kind of makes sense. So that's the introduction to the math and the concept behind linear regression, as well as that of parametric learning. In linear regression, we're simply fitting the best line across a number of points, trying to minimizing the sum of squared errors there.